Right? Okay.
All right. So, last thing we got to cover on probability, and then again, you got to be able to mix them all up. So we're back to independent, dependent, which we already talked about on the first day. Do not zone on me. Stay with me. Okay? Back to independent, dependent, which you did on the first day. What do you remember about independent as of the first day? Yeah.
Usually if it's in the independent problem, it says like, we'll pick a coin and put it back.
Like a replacement thing, right?
Replacement.
Because why? Because what does that mean for us?
That means that you're not changing the thing.
The original probability, right? Is not, so the second time you go to do something is not impacted by what you did the first time, right?
Yeah.
Whereas if you don't put the coin back in, the probability now changes of you getting whatever it is you wanted to get originally, okay? And that was your and situation. Is everybody okay with that? Okay, so you might be able to, like we did on the first day, might be able to read the problem and just say, okay, well, I'm not replacing, so therefore it's dependent, okay? Probably not going to happen on the Regents exam, just saying, okay? But it is a possibility that you could just read and interpret it and say, okay, this is dependent, this is independent, I'm multiplying together to get my and, all right? So that's still on the table. However, what they're really looking for is more of an analyzing something where you're not sure if it's independent or dependent and deciding. All right, so that's what we need to talk about today. How do we do that? How do we decide based off the given information if it's not just point blank readable? How do we decide whether it's independent or dependent? Okay, so part of it comes from the definition, which we did on the first day. And we said that if events are independent, and we want to know what the chance is of both things happening, this and this happening, we multiply the two probabilities together. Right? Everybody's okay with that? All right? So, if you read this, when a car is brought to a repair shop for service, the probability that it will need the transmission fluid replaced is 0.38 or 38%, right? The probability that it will need brake pads replaced is 28%. The probability that it will need both transmission fluid and brake pads replaced is 16%. Let the event that the car needs transmission fluid replaced be T. The event that the car needs brake pads replaced be B. Are the two events independent? So by reading it, it's not straightforward like the ones that we did at the beginning. Okay? But if they are independent, right? Let's just say, let's assume they're independent. And if they are independent, then this definition has to hold. Do you guys agree with that? That has to be true. It's like in geometry. If I gave you a triangle in geometry and I said one side is 3, one side is 4, and one side is 5. Is this a right triangle? What could you do to justify that it was a right triangle? Pythagorean theorem, right? You plug the info in, and if it works in the Pythagorean theorem, you're like, it's a right triangle. Correct? Well, that's what we're doing here. Okay? So we know if it's independent, this definition has to hold. Okay? So if independent, then probability of A and B happening has to equal the probability of A times the probability of B. That is how you define independent. Okay, so if that's the case, then here, what do we know? Well, we already know we've got brake pads and we've got transmission, right? So what's the probability that you're going to need transmission fluid? Well, it's 38%, right? 0.38? Okay, so we'll call that probability of A. All right, you want me to fill in letters for T and all that? I'll do it. Probability of transmission and brake would have to equal probability of transmission times probability of brake pads, if you want to use the letters they give us, correct? And the probability of you needing your transmission replaced is 0.38, given. And the probability that you're going to need brake pads, given to you, 0.28. They also give you what? They give you the probability that you will need both transmission fluid and brakes replaced, correct? And that's 0.16. So can't we just check and see whether these are independent or not based off the definition? Does that make sense? Plug it in. I already know this is supposed to be 16%. The question is 38% of 28%. What does that give me?
10.64%.
So point and what?
Oh, it's 0.1064.
64?
Yeah.
Okay, so are these equal? No. So then what do we say about these events? They are not independent or they are dependent. You guys kind of following that? Straight up off the definition, if they give you everything you need. Okay? So we would say, since the question was whether they are independent. All right. Questions on that? We're good. Okay. Second way to look at this. So when this is my definition of independent, but probability of A and B right here, and probability of A and B over here would be the same thing, correct? Okay? Except this is the dependent version. All right? And take a look at this says, we already know what this means, probability of B following A. All right, so let's just look at that for a second. Probability of B following A has happened, right? Because if it's dependent, it was affected by something, right? So the probability of B happening following A, does that sound familiar at all? Probability of getting B following that A has already happened. Yeah?
Sounds like we did.
The given we did yesterday, correct? That same idea? Given this has happened, okay? So this is really probability of B given A, is what they're really saying there. All right, so we're going to relate the two. Based off of what's up above, you could say probability of A and B equals probability of A times probability of B. But this and could be replaced with what was up above. It could be replaced with probability of A times probability of B given A. Because this is also probability of A and B from up above. Right here. That's really this. And that means I could divide both sides by probability of A. Cancel, cancel. And that tells me that the probability of B given A, when it's equal to the probability of B, guarantees independence. Because this was coming from the definition of independence. Okay, so this is another version. This also shows independence. So if they are equal, if the probability of B given A is equal to the probability of B, then they are independent events, by definition. We've got different ways to look at these. All right, so conclusions. All right, so we've got. All right, first day, read the problem. And interpret. That was day one. Read the problem, says something about replacing, not replacing, and you can tell based off what they give you. Again, probably not what they're going to give you on the Regents exam. And they like these, so I'm just telling you. It's showing up on a regular basis, independent, dependent stuff. Second one, straight from the definition, right? Probability of A and B happening would have to equal the probability of A times the probability of B. If that's the case, and they are equal, they are independent events. Aiden, you should be writing this stuff down. Third possibility, you do probability of B given A, and it equals the probability of B. If that happens and they are equal, they are independent events. So all of this is checked for independence, which ultimately will also check for dependence. It doesn't work. Or, you could also say probability of A given B, but what do you think that would have to equal for it to be independent? Probability of A. So any of these ways, most specifically these three, right, because they're based off the things they usually give you, any of these would be, you could use to justify independence. Okay, now you might need one versus the other. If you might have options, you may be able to pick whatever makes more sense to you, or you might want to pick one because of what they give you. Okay, like that first one was nice to use the definition because they gave me everything I needed, I plugged it in and I was done. Questions so far on what we're talking about? So here's what I would require. Okay, when you're trying to prove independent or dependent, you're writing whichever method you're using out like in a formula base. I don't care if you use the letter T and B if that's what it's in the problem, but you're writing this out first and then you're plugging in your numbers and values to show whether it's yes or no type thing. Okay, is everybody right with that? Don't just plug in numbers. Show me which one you're using. Good? Michael, good? You look like
You get the memorize this?
you do. Not given to you. Pretty much nothing's given to you in this course, right? I mean, pretty much nothing in that reference sheet. Alright? Questions? That's really it. We're just going to practice now. Okay? Let's practice. Alright. You have your table, which we've been working on. A survey was taken to examine the relationship between hair color and eye color. The chart below shows the proportion of people surveyed who fell into each category. If a person was picked at random, find each of the following conditional probabilities. Show the calculations used. Okay, so find the probability the person picked had brown eyes given they had blonde hair. That was yesterday, correct? Who can do this for me? Don't jump in once. Nick, tell me what I'm doing with the chart. Where am I looking?
So since it's given that they have blonde hair,
Okay.
you can only have it out.
Blondes, right? So I need to look at this column only, nothing else matters to me.
Right.
Okay, so now what do I got then?
So it's, what is it, brown eyes?
Brown eyes.
0.10.
So 0.10, because that's the only place in the column that has brown eyes. Yep.
Over
Over
0.35.
0.35. Everybody's good there? That was last night's. Go to your calculator, type it in, let's get our number. If math entering makes you go back to a fraction so I don't have to write a big long decimal, that would be good. If not, I'll write out the decimal. Think you got anything for me?
2 sevenths.
2 sevenths? Does it come out to 2 sevenths, or do you have to convert it back?
No, 2 sevenths.
Okay. So if anybody's got a decimal, it should convert it back to you for 2 sevenths. Which, just for this case, what is that as an approximate percent?
29 if you round up.
20, nearest 10? Where do you go?
Nearest 10 would be 28.6.
Okay, so just to kind of think through the problem, you have a 28.6% chance of picking somebody with brown eyes given they have blonde hair. Are we okay with that? That's last night's stuff. All right. Find the probability the person had red hair given they had green eyes. Quinn, tell me what I'm doing.
Okay, so you'd have to only look in the green eyes.
Only looking at green eyes. Okay, so only looking at green eyes. Got it.
Yeah, and it's red hair, so it'd be 0.15
So 0.15,
Yeah.
because that's the only one that has red in that column, right?
and then over 0.25.
0.25. And do I get a fraction of it, or do I need a big long decimal?
It's 0.6.
0.6. Okay. So I don't have to write this fraction. So approximate, well, it's not approximately, exactly 60% chance of that happening. Good. Okay, so third part of this, the new stuff. Does having red hair seem to have some dependence on having green eyes? Okay, like is there some kind of relationship going on that might be worth studying and doing a statistical analysis and see, right? That's like what they're trying to figure out, okay? Do I bother doing some kind of study? Is there some kind of relationship maybe going on here? All right, so look, I already know the probability of me picking someone with red hair given they have green eyes, correct? And that's a 60% chance, right? What if I just pick out of the people that I've studied, people with red hair? What's a chance that I get somebody with red hair? In other words, if I want to know if this is independent, okay, I could say, like, does green eyes and red hair have anything to do with it? I could take what I've already done, which is one possibility, red hair / green eyes, and if it's equal to the probability of having red hair, period, with no restrictions, then I know they are independent events. Because that's the definition of independent. Okay? So we already know this is 60%. What's the probability that you will pick somebody with red hair based off your chart? What is it? 20%. Do we see that in the chart? Chance you're gonna get red hair, period, don't care anything about them except they have red hair. 20% chance. So what does that say to you?
It's not independent.
It's not independent. There's something going on. There's some kind of dependence here. Okay? Because you're 3 times more likely to get somebody with red hair if you start with people with green eyes. That seems pretty, there's something weird going on, right? Maybe it's genetics, maybe it's something else. You guys understand what they're saying to you here? Okay? So these are not independent events. Seems like there's some kind of connection here. All right? This is because this is approximately 60%. These are not equal, 20%. Okay, so does that quantify your, so you might write something like the chance of picking a person given Yes.
I thought it was like you do the probability of like A and B equals P and
So you could have done that also. Remember I gave you 4 versions, okay? The reason I went with this one is A, I had already done half of it up above. And because, like I could have also done probability of green eyes given red hair. And then done probability of green in comparison. Okay? I'm not going to get the exact same numbers here, but I'm going to get the same results. They're not going to be independent events. Okay? And they're probably going to be spread pretty far. All right? If you do it this way also, if you do probability of red and green happening, right, equals probability of red times probability of green, right, which is another version. You could get that info from your chart as well, right? Probability of red and green was 15%. Probability of red was 20. Probability of green, so 20 of 20, 20 of 25. What do you got? 20 of 25. 20% of 25.
0.05.
0.05. Still clearly not equal, and still 3 times. You know, right? You still see a big discrepancy. So you'd still be saying that would be your work, still justify it the same way. Okay? Still not going to be independent. All right? Questions on that? Okay. So same idea here. You've got a survey, a bunch of 6th graders. Math, social studies, I guess this doesn't add up to 10, so you can throw that in there. Does it appear, based on the data in the table, that the preference for math as a favorite subject has dependence on the student's gender? Are you going to like math more if you're a male? Are you going to like math more if you're a female, right? Is there something going on here type idea? How are we going to check to see if gender has any impact, what you think based off your study?
The, whatever, checking if it's not going to be kind of thing.
Yep, so what do you want to do?
The
Probability of,
A and B.
okay, but I'm not using A and B because I got things going on here.
You have to convert some of them into the probability. Like,
Yeah, but I can do that as I'm doing it. I get what you're saying.
right.
Someone help, oh, go ahead, you want to keep going?
Well, which part are you asking?
I'm looking for what I can do, like, pick a way here. What do you want to do? How are you going to show me, based off this info, whether gender has an impact on whether you like math?
Total students who actually like math is 18 out of 57.
Okay. So you're going to go probability of liking math equals what?
0.3158.
Okay, but what are you comparing it to? You know what I'm saying? Like, okay, help him out.
Total.
Help him out. Help him out. Anybody? Really, no one? Chris?
Probability of liking math. Alright, is equal to the probability of liking math given boy.
or given male or given female. Do you kind of see what he's saying? So he's choosing to go by a given method. Again, there's different ways to do this. He's saying, what's the probability you like math given you're male, let's say? Right? One possibility. Okay? And what would that have to equal if this is an independent event, if there's no dependency on it? What would it have to be equal to? Yeah.
Probability of liking math.
Probability of liking math. The top one, right? That's your probability of A/B equals probability of A. Okay? So this would mean probability of liking math. So this is one thing to check to see what's going on here. Okay? What's the probability of picking someone who likes math given they are male? Right? So we go to our chart. Probability they like math given they are male. Okay, well I'm only allowed to look at males, right? And they have to like math. So I have a 10 out of 27 chance of that happening. That's the stuff you did last night. Now, what's the probability that you, if you randomly pick someone that they like math? Period. That's all you care about. Carolyn, sorry. Carolyn.
18 over 57.
18 out of 57. Okay, go to your calculator, because probably to compare these don't have common denominators, so type them in and get a decimal so you can compare. What are we getting over here? Point,
0.37.
what is it?
0.37, and then there's a lot more.
Give me a couple more.
0.37. 0.37.
So it's repeating?
Yeah.
Oh,
Well, no.
no.
0.37, 0.37, 0.4. So 0.37 repeating, sorry.
Okay. Equals 18 over 57?
0.315789.
Good enough. Independent or dependent?
Independent.
What does it require for them to be independent?
Oh, dependent.
Gotta be the same, right? Are these equal to each other? They're close, but they're not equal. Okay, so these are not equal. So these events are not independent. Or in other words, they are dependent. Now, I would say there's not as big of a difference as there were with the green hair and the red eyes, right? So maybe there's not, if there's like a slight dependence here, right? There's not probably a lot going on, okay? But it's still dependent. Are we okay with that? Has to be equal to be independent. Yep.
How would you do with probability of A and B equals probability?
So that would be possibly probability of math and male, right? Would have to equal the probability of math times the probability of male. Your numbers will be a little different, but they still won't be equal. Okay, so your result will be the same. Are we okay with that? Or you could have done what? You could have done probability of math given female. Female given, right? There's different ways to do it. Yeah.
So, our next unit is stats.
It is.
So we're gonna have to do like standard error, like deviation and stuff.
We do have to do standard deviation, yes. That's not the hard part though. Don't move me ahead yet. Alright, ready? Does it appear based on the data in the table that the preference for social studies as a favorite subject is dependent? Okay, so now we're doing the same idea with social studies, right? So let's go probability of picking someone who likes social studies given, we'll go male again, given male. What would that have to equal for them to be independent? Probability they like social studies, right? Okay, probability of social studies. So probability of social studies given male is what? Maggie, you got it?
9 over 27.
9 out of 27. Probability of just picking someone who likes social studies?
19 out of 57.
19 out of 57. Okay, so what are we getting for 9 out of 27? So 3 repeating, or 1/3. Okay, and what are we getting for 19 out of 57?
Also true.
Also a third. So what does that tell us about social studies and males? Independent. And you would get the same for females. It's not going to change. The numbers might be a little different, but you're going to get the same results. Okay? So we would say liking gender and social studies are independent events. Yeah.
For the way that I did it up there,
Mm-hmm.
would it be, like, for instance, probability of social and male
Correct.
equals probability of social times
Probability of male. Yep.
Which would be, then, probability of 9 over 19.
I don't know offhand. It didn't work out to be independent?
No.
Okay, let me check it later, because I gotta finish in 2 minutes. Let me do one more. And then if I don't, I promise I'll get 2 points. Okay? Given events A and B such that the probability of A equals 0.6, probability of B is 0.5, and probability, what's that mean? Yeah, or. That's union. Okay, we talked about that yesterday. That was a little symbol. That's or. And the probability of A or B is 0.8. Determine whether A and B are independent or dependent. Everything we've done has been off a chart, correct? So you should be able to draw your own chart. We worked on that. So if my chart would look something like A, not A, total. B, not B, total. Right, just to get a visual of what's going on. They're telling me the probability of A is 0.6. Okay, A is here, so probability it happens, 0.6, or 60%. Probability of B happening, 0.5. Probability of A or B. Well, if it was probability of A and B, I'd be all set, because it would go right there, correct? But probability of A or B, that's where we start talking about mutually exclusive, right? All that stuff. Okay? Or means I do what with my probabilities? Add or multiply? Add, right? So if these were mutually exclusive, which they don't tell me, but if they were, I should be adding those together, correct? To get the total probability? I'm coming. So the probability of A or B, right now, looks like it would be 0.6 plus 0.5. So the probability of A or B would be 1.1. Does that make sense? No, because they're telling me the probability is 0.8. So what does that mean for me? They're not mutually exclusive. Do you guys agree? Right? There's overlap. How much overlap? How do I know how much overlap there is? Subtract them, right? What's the difference between these, right? So if I subtract them, 1.1 minus 0.8, that tells me that there's 0.3 that they both have. So where's 0.3 going in my chart? For both. You guys kind of follow me there? On how we fill in our chart. Now we're to the point where we can do what we've been doing before. If you want to do independent and dependent, you've got choices. I'm going to go, since I got straight up info, I'm going to go right off the definition. I'm not going to bother doing the givens. You guys all right with that? So I'm going probability of A and B equals probability of A times probability of B. Because I got it right here in the chart. I got everything I need. So 0.3 would have to equal 0.6 times 0.5. And when I put in 0.6 times 0.5, what's going to happen? 0.3, right? So what's our conclusion here? Independent or dependent in this case? Independent, because they are equal. That was quick. I'm going to take your instructions tomorrow. I'm not looking, I'm sorry. But we did it here, too. Okay. Anything, real quick? Okay, I should be after school. I should be back. I just have to go to the doctor's real quick. You have a couple minutes to start working on your homework.
I know she's leaving.
Is someone else coming for the next period?
I would hope so, yeah.
Okay, thank you, because that's a test. I'm going to leave this, there's tests.
Okay,
So I just don't want to leave the door open with, for next test, for next period.
All right.
Okay, thank you.
sure, I'll wait till I get it.
Okay, thank you.
Mhm.